listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and our very own Worth Electronic technical specialist. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. During the design cycle, when you go to implement your connectors, you have to ask yourself, what is the working current? Now, this is the maximum current that can be used for this connector at any time for any duration. This current brings temperature rise through the Joule effect, and for specific applications such as motor starters and capacitance discharge, it's recommended that you use a higher current than usually accepted by the other connector, and only for a short time. In today's podcast, we'll discuss what values need to be considered when selecting a connector, and also discuss reasonable temperature rise and the lifetime of the connector.
I will talk about you today about the inrush current. That is a running question that is coming from the market, from you. So I think this would be very important to talk about that today. An application note will be released in 2 or 3 weeks about that, so you will be able to find it in our website really soon. And of course, at the end, you will have this presentation. So the question about inrush current is here. What is the good question? You want to develop a system and with a current of, let's say, 5-6 amp. Then in your PCB, you choose a simple TBL terminal block, the pitch 2.54. So this is small, and then you have a small space booked in your PCB for that. So you're happy, this is small, and of course, a small product is not so expensive. So everything is okay, but you realize that this is for a motor power. So here, 6 amp for the steady state, everything is okay. The TBL, the terminal block, works really properly, but you know that during the starting point for a motor, then the current could be multiplied by 2, 3, 4, 5, and even 6 times the stable current. So that means that during the short time, a very short time, you will have around, depending on the motor, depending on the situation, application, etc. But let's say this is roughly 6 times the stable current. So during a short time, you will have 6 times the stable current. So here, do you have to buy a higher terminal block for that? 6 times by 6 is 36, so the higher terminal block is 57 amp in our range. But this is a pitch of 10.16 millimeter. The size is bigger, so your PCB will be bigger, your application will be bigger, and of course, the price of your connector will be bigger too. Is it the right answer to this question? Normally, yes, but this time, I hope you will have another solution, because this is the case for a motor. An electric motor, you have that in that kind of application. E-scooter, you can have a transformer, you have a capacitor application, lamp like this one, tungsten lamp, or Wi-Fi power delivery like an inductance like this one. We did a market study because the problem is here, how to put inrush current in terminal blocks. But how do you know? How do we know the exact number of amp for the certain time? We did a market study, and I will show you just 1 or 2 examples that is written on standard. We used this standard for mechanical switches. And here, mechanical switches is usually to power motor or that kind of thing. So this is very useful. And in that standard, for example, you see that for resistive motor or motor with locked rotor, then you multiply by 6 the stable current. And the same for inductive load, you multiply by 6 the rated current. And this is even higher with a tungsten filament. Okay, tungsten filament is an old technology. Now we all have LED, or most of you have LED in your at home. But for tungsten filament, you multiply by 10, even 16 times the stable currents for a duration of 50, 100 milliseconds. This is not written in this standard, but you have capacitance discharging too, which is a problem, and it creates inrush currents. So with all the standards we have and the market survey we did, then we created that curve. And here you have the time in seconds, and here you have the inrush current peak ratio with the rated current. So what does it mean? It means that, for example, the customer, they say to us that they want to use 2 times the rated current. So in this example that we had at the beginning, so this is 6 amp multiplied by 2, so 12 amp during 6 seconds. Is it really possible? We'll see. But initially, we have to go a little bit through a theoretical point. Don't worry, this will be really fast. So a connector power is only a resistance. I mean, a connector that is working properly. A connector that is working properly has the behavior of a simple resistor. A simple resistor had an internal temperature as the same ambient temperature, which is T. If you put current in it, so I guess that most of you know that this is called the Joule's effect, then you will release heat in the environment all around the resistor. This is called the temperature rise that is noted delta T. So the internal temperature of the connector is given in degrees Celsius, is the ambient temperature plus delta T that is given in Kelvin. Why this is given in Kelvin instead of degrees Celsius? It could have been given in degrees Celsius, but here this is given in Kelvin just to make the difference between an absolute temperature and a temperature rise. This is the only reason, and this is why you will see that in most of the literature and the standard. How to estimate the delta T, the temperature rise? This could be calculated with this formula. Delta T equal to a constant K. This constant K is given by the environment, so with a lot of parameters. The size of the resistor, the color of the resistor, if it's in a closed box or in still air, in a lot of parameters. We will not talk about that today because this is really another question. And here, most important is that the temperature rise is proportional to the resistance here. And most important here is proportional to the square of the current. The temperature rise in a resistor, and so in a connector, is proportional to the square of the current. What does it mean? It means that if you double the current, you will multiply by 4 the temperature rise. That is the law, how it works. And so if we are talking about the same connector in the same environment for 2 different currents, so there is a relationship between the ratio of the 2 temperature rise here and the square of the current. And I wrote here not equal, but roughly equal, because when you modify the temperature, then the resistance, the value of the resistance will change. That is the rule of the nature. That is always like that. When you increase the temperature, then the value of the resistor will increase. But that means that if you have the temperature rise at 1 current, then you are able to estimate the temperature rise at another current. So for a terminal block, the UL 1059, if you know, gives that at a rated current, well, the definition of the rated current for a terminal block is that the delta T, the temperature, must be below 30 Kelvin. So, for example, in this example, you have an ambient temperature at 50 degrees Celsius. So the internal temperature at the rated current will be maximum 80 degrees Celsius. But of course, if you put the rated current, this maximum temperature rise will not happen in 1 second. It will take a certain time. This curve shows here the time that will take this example to grow until you reach a stable state. And so if you increase the size of this graph here, you can see that, for example, at the rated current, in 10 seconds, you will reach only the temperature rise of 5 Kelvin. So you can easily imagine that if you have a higher current than the rated current, you will reach a higher temperature rise, but it will be always below 30 Kelvin. So how do we know exactly how it works? So we need to do tests. So this is just an example. We took a terminal block, TBL, 20 AWG, the wire length at 50 centimeters, and we put the rated current of 5 amps here. This is the blue curve. You can see that this is the time in seconds. So after 3 minutes, you don't reach the stable state, okay? And you will see, you can imagine that even after 10 minutes, we will be below 30 Kelvin. This is the standard. But here, 8 amp, you go faster and you increase the temperature of higher than 30 Kelvin, obviously. That's the same with 11 amp. And just to make you know that the relationship with the square of the current is okay, is that here you have 5 amp and you reach a temperature rise of something like 18 degree and 18 Kelvin, and 11 amp is a little bit more than 2 times the rating current. So you multiply by more than 4 times the temperature rise here, and you reach here a temperature of 62, 3, 4, I don't know exactly, but this is roughly 4 times this temperature. So this is working. And here, the more you increase the current, the speeder you will increase the temperature rise. And of course, at a current of 35 amp, we stopped the test very quickly, because if you go too high in temperature, then you will be in trouble with the connector. So now, for example, if we take this at 11 amp, so this is a ratio of 2.2 with the rated current, so you can use it during 35 seconds to reach a temperature rise of 30 Kelvin. So we can create this curve. This is the tested current ratio at 30 Kelvin maximum. For example, here we take that point. We have a ratio of 11 amp divided by 5. This is 2.2. And then we can put that point. That point means that during 35 seconds, at a ratio of 2.2, then you have a temperature rise of 30 Kelvin. And with all the other curve, we can put different points. So this curve is the time that you can put a current ratio in the connector, in this connector, without exceeding a temperature rise of 30 Kelvin. So now, what is the goal of the test? Is to have finally that curve, that is the market survey, and that is the reality. So if you put these two curves in one single, then you can see that, fortunately, we have a security margin between what is requested from the application and what is possible. And we are happy because we like to work with security margin. And roughly the security margin between what is measured and what is needed is roughly 3. Okay, so we can feel that initially this could be possible. So here we put 10 big spots here in that curve. This will be the 10 spots we will test in our connector. That is a big table, but really basically just to show you all the tests we did to have that final curve. Here, 1, 2, 3, 4, 5, 10, 6, 7, 8, 9, 10 current ratio with the time. So from 1, so this is the rated current, up to 16 times the rated current, but only during 0.1 second. And here you can see that is all the tests we did with limited number of poles, 2 poles, up to the maximum number of poles, which is 24 here. Okay, and what is the result? So some picture, we used thermal camera to do the test. Here you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points here that show you that you have all the results for just one connector. Of course, I will not show you all the results. This is not really interesting. But this curve is interesting. And why this is interesting? Because the first one here lasts 10 minutes, and this is only the rated currents. And as you can see, the rated current here has the highest temperature rise. And this is not a stable state here, but you can imagine that if we continue, we will be maybe around between 20 and 25 Kelvin, which is lower than 30 Kelvin, so we respect the standard. But after that, all the inrush currents here are lower than this big curve here. And especially if we take the ratio of 16 times the rating current during 100 milliseconds, you have a temperature rise of around 5 Kelvin only. We can feel that this will be possible to use this curve. But be careful. Here we have a time gap of 5 minutes between 2 inrush shots. That's really important that, of course, you will increase very fast the temperature. So you need to let the temperature decrease between each shots, inrush shots. Otherwise, you will add and always add temperature rise until you reach a too high temperature. So this 5 minutes depends, of course, on your environment. This is the choice that we had for that in a still air. Okay, so now we know that for all the connectors, all the terminal blocks, we can use this inrush peak current ratio. So here you have the time in seconds, you have the current ratio, and here this is exactly the same curve, but in a shortest time. You can go from 0.100 milliseconds up to 1 second. So it means that you are able to use during 100 milliseconds 16 times the rated currents. And for example, during 1 second, you can use 5 times the rated currents. Okay, but depending on the operating temperature. So that's good news. We know now how to use the inrush currents, but you have to look to your environment too. Here, always the base principle is to keep delta T temperature rise always below 30 Kelvin, and always keep the internal temperature below the operating temperature that is written on the datasheet. That's why we have currently an application node that is called the rating curve that already exists. You can find it on our website. That is for the UL rating curve. Here, you can use, of course, 100% of the rated currents until you reach a certain temperature. For example, Let's talk the example of a connector that is able to have, a connector that has an operating temperature of 85 degrees. So you do not have to exceed 85 degrees. So you take 85 degrees, you have to stop the current here. 85 degrees minus 30 Kelvin, this is 55 degrees. So after 55 degrees, you have to decrease the current until you reach this 85 degrees. And you've got one single curve for each maximum operating temperature. Maybe you know that one of my colleagues explained everything about that yesterday. But if you want to use this curve with the inrush current, then we have to be careful. So we decided to split this 30 Kelvin in two. So 15 Kelvin for the stable current and 15 Kelvin for the inrush current. What does it mean? It means that this is the curve without inrush current, and this is the curve with inrush current. So here, 30 Kelvin, if you limit the temperature rise at 15 Kelvin, then you can use the formula I showed you 10 minutes ago. So the current maximum at 15 Kelvin is the square root of the ratio between 15 and 30 Kelvin multiplied by the current maximum at 30 Kelvin. So you have to limit your stable current at 70%. And then here, you use it until you reach the temperature of 55 degrees Celsius for a maximum operating temperature of 85 degrees Celsius. And then you have to decrease the current until you reach the temperature of 70 degrees. And then at this point, you still are able to use the inrush current until 85 degrees. I hope this is not complicated for you. This is not easy to explain and maybe not easy to understand. I don't know. You will have the presentation at the end. You can ask me questions at the end or anytime you want by email or to your local FIE. But at the end, you will have these two curves. You can use these two curves here, the inrush current, and you have to limit the stable current with this derating curve. But be careful. All these tests was done in still air. You saw that this is with simple PCBs. So with your system, I don't know, maybe it will be in a closed box, maybe you will have a fan, maybe you will have anything, big aluminum radiator, I don't know. Maybe you can do better, or you have to limit the inrush current. So that's why I put this in red. Always do a test to check temperature of your system before releasing it. This is very important. Everything I said is true for all the terminal blocks that we have in our range. And if you want to test different applications, different products, I don't know, then you can be in touch with your local FIE, local application engineer. We can do the test for you because we have an application lab in France. Yeah, I forgot to tell you that I live in France, in Lyon. And we will be happy to do the test with you or for you.
You can view the entire line of Worth Electronic connectors and other electromechanical components available at Worth Electronic online. And for any questions you have, click the icon to talk with our live chat team. To view the materials and replay the video, check out our YouTube page or our new video center at www.we-online.com. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.